Hey guys, this is IBM with another episode of Learning Physics. This is magnetic fields and electromagnetic induction, and I think this is going to be part 20 of the solved past paper questions. So in part 19, we stopped on question 57. In part 20, I want us to start from question 58. An incomplete diagram for the magnetic flux pattern due to a current carrying solenoid is illustrated here. Okay. On the figure, draw arrows on the field lines to show the direction of the magnetic field. Of course, the field due to a current carrying solenoid is similar to that of the poles of a bar magnet. If you look at the bar magnet, the field lines are concentric. The field lines of a solenoid are similar to those of a bar magnet. And if one side is north and another side is south, you know that field lines originate from north and terminate to the south. So they are similar to those of a bar magnet, with one end of the solenoid being north and one end of the solenoid being south. Now we imagine gripping our solenoid in our right hand, and the thumb points towards the north end of the thumb points towards the north end of the thumb points towards the north end of the magnet or of the coil, because I said it behaves as if it's a magnet, with one end being north and the other end being south. So imagine gripping your conductor with the fingers folding in the direction of the current, as illustrated by this diagram here. You grip the conductor using your right hand, and you notice that the fingers fold in that direction, the direction of the current. So the current goes back to the back, and it is in this direction here. So the fingers must fold in this direction here. And when you grip your coil in your hand, you notice that the thumb points to this side, making this north and making this south. And you and me know that the field lines originate from north and terminate to the south. So the arrows should be pointing towards the south, like this. The arrows should be terminating to the south end of the coil, and should be originating from the north end. So this side, they should be pointing in this direction. Just like that. So that is the field pattern. I want you to note that the field lines on a bar magnet originate from the north and terminate to the south, and that is very important for us to think about a solenoid if it is behaving as if it is a magnet. State the feature of figure 5.1 that indicates that the magnetic field strength at each end of the solenoid is less than at the center. So at the end of the solenoid, you notice that the separation of the field lines is greater at the ends of the solenoid, yet the separation at the center is very close, is very small, and yet strength of the field lines is indicated by the separation between the lines. So we shall simply say that the lines are more spaced. Lines are more spaced out at the ends. At the ends than at the center. So you can also check the field lines are further apart at the ends than they are at the center. So it means the field is weaker at the ends and stronger at the center. A hole probe is placed near one end of the solenoid in A, as shown in the figure. The hole probe is rotated about the axis XY. State and explain why the magnitude of the hole voltage varies. So the hole probe is being rotated at this end here about the axis. Remember, the hole voltage depends on the angle between the magnetic field and the plane of the Hall probe. As the angle varies, the Hall voltage also varies. So we shall simply say that the Hall voltage depends on the angle between the magnetic field and the plane of the Hall probe. We have answered a similar question earlier on. So we say that the Hall voltage depends on the angle between the magnetic field and the plane of the Hall probe, the plane of the probe or the plane of the Hall probe. So the Hall voltage is going to be maximum when the plane is perpendicular to the magnetic field, and the Hall voltage will be zero when the plane is parallel to the magnetic field. So I would say the Hall voltage is maximum when the field is normal to the plane of the probe, and the Hall voltage is zero when the field is parallel to the plane of the probe. Then state Faraday's law. Like I said, every time I restate this law, it's because I want to use it to explain something. State Faraday's law of electromagnetic induction. We say that the magnitude of the induced e.m.f. is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced e.m.f. is directly proportional to the rate of change of magnetic flux linkage. The Hall probe in B is replaced by a small coil of wire connected to a sensitive voltmeter. State 3 different ways in which an e.m.f. may be induced in the coil. So the Hall probe is replaced by a small coil of wire connected to a sensitive voltmeter. So we expect that the voltmeter is most likely going to give a reading if there is a change in magnetic flux linkage. So state 3 different ways in which an e.m.f. may be induced. So to induce an e.m.f., we need to cause the change in magnetic flux linkage. The first thing we could do is maybe we rotate the coil. So rotating the coil, because we have a DC, a direct current in the solenoid, rotating the coil will cause a change in magnetic flux linkage, thereby inducing an e.m.f. Number 2, we can vary the current in the solenoid by increasing its value or decreasing the value. Vary the current vary the current in the solenoid. By increasing its value or decreasing its value, we are changing the magnetic flux linkage, or we can turn on, turn off, and on the current in the solenoid. Of course, when the current is turned on or off, there's a change in magnetic flux, which causes a change in magnetic flux linkage. Alternatively, we can also move the coil towards or away from the solenoid. So in the process of moving the coil, of course, the field weakens as we move away from the solenoid. So it means that when you move the coil towards or away from the solenoid, there is a change in magnetic flux linkage because the magnetic field is not constant towards and away. It becomes weaker as we move away from the solenoid. And another one could be maybe inserting an ion core in the solenoid. That, remember, the ion core concentrates the magnetic field, thereby increasing the magnetic flux linkage, increasing the magnetic field strength, and increasing the magnetic field strength would imply an increase in magnetic flux or a change in magnetic flux linkage. So we could insert an ion core into the solenoid. Even though the current in the solenoid is constant, inserting an ion core makes the magnetic field around the ion core, around the solenoid, to rapidly grow. So all the above result in a change in magnetic flux linkage, of magnetic flux linking the coil. Thus, an induced EMF is going to be generated in accordance to Faraday's law. A charged particle of mass m, charge minus q, is traveling through a vacuum at constant speed v. It enters a uniform magnetic field of flux density b. The initial angle between the direction of motion of the particle and the direction of the magnetic field is 90 degrees. So that means when it enters the presence of the magnetic field, the magnetic field is perpendicular to the direction of the velocity. Therefore, the particle experiences a magnetic force. Explain why the path of the particle in the magnetic field is the arc of the circle. Of course, the magnetic force is constant and is always perpendicular to the direction of motion or the velocity of the particle. So the magnetic force does not change the speed, does not change the kinetic energy, there is no work done. Therefore, it just provides centripetal force. So we say the magnetic force is constant and always perpendicular or normal to the velocity, or it is perpendicular to the direction of motion of the particle. So this magnetic force does not change speed, or it does not change kinetic energy. Of course, if there is no change in speed or change in kinetic energy, there is no work done, but just provides the centripetal force. Just provides the centripetal force, or you can call it centripetal acceleration. So the magnetic force just provides centripetal acceleration. The radius of the arc in A is r. Show that the ratio Q over m for the particle is given by the expression Q over m equals to V over BR. I think we have answered a similar question earlier on. So magnetic force equals to the centripetal force. That means that B QV equals to m V squared over R. So rearranging this equation here, you notice that B times Q is the same as mV over R, which when you rearrange, you notice that Q times R, BQR is equal to mV. So you have that Q over m is equal to mV divided by, it is m, it is V divided by Q over m is equal to V over B times R. The initial speed v of the particle is 2 times 10 to the power of 7 meters per second. The magnetic flux density B is 2.5 times 10 to the power of minus 3 teslas. The radius r of the arc in the magnetic field is 4.5 centimeters. Use this data to calculate the ratio Q over m. So Q over m is equal to V over B times R, which is going to be V is 2.0 times 10 to the power of 7. Then B is 2.5 times 10 to the power of minus 3 teslas. Then times R, which is 0.045, to change it to meters. So from my calculator, we have 2 exponent 7 divided by 0.045 times 2.5 exponent minus 3. So that's 1.777 or 1.8. So this is 1.8 times 10 to the power of 11. Yes, coulombs per kilogram. The path of the negatively charged particle before it enters the magnetic field is shown in the figure here. Note that the particle is negative. The direction of the magnetic field is into the plane of the page, which means if you are using Fleming's left-hand rule, the first finger must point into the page. On the figure, sketch the path of the particle in the magnetic field as it emerges from the field. So because the magnetic field is into the page and the particle is towards the right, that means the direction of the magnetic field, which is into the page, is perpendicular to the velocity of the particle. Remember, the particle is negatively charged, so it means the second finger, which points in the direction of the current, must point in the opposite direction to that of the negatively charged particle. So the second finger points in the opposite direction with the with the first finger pointing into the page. When you use your left hand to make the second finger to point in the opposite direction to that of the particle, and the first finger to point into the page, the thumb is going to point to the bottom of the page as illustrated there, which means that the path of the particle is towards the bottom of the page. So you draw a very smooth curve. And of course, when it emerges, This part here, when it emerges, it is supposed to be a straight line. So you put a ruler and draw a tangent to the curve. At that part where it emerges, I'm saying this part should be straight. Now, normally students make a mistake and make this to be a horizontal line throughout. I want to depict that the path actually curves. As soon as the particle enters the field, like that. And I say this part here should be a straight line, which should be a tangent, a perfect tangent to the curve. So use a ruler and draw a straight line, not bending. It should be a perfect tangent to the curve. Okay, so the path should be towards the bottom of should be towards the bottom of the page. Do not be tempted to draw a straight line, it is actually curve. A long solenoid has an area of cross-section 28 centimeters squared as shown in the figure here. A coil C consisting of 160 turns of insulated wire is wound tightly around the center of the solenoid. The magnetic flux density B at the center of the solenoid is given by the expression B equals to mu naught Ni. Of course, N is not given in the list of constants. That means this was an old past paper question. Therefore, I just quoted the value of mu naught, not N naught, mu naught, just for learning purposes. But still the same question can be set where mu naught is quoted for that particular question. I is the current, N is the constant, which is equal to 1.5 times 10 to the power of 3 per meter, and mu naught is the permeability of free space. Permeability of free space is 4 pi times 10 to the power of minus 7. Calculate for a current of 3.5 amperes in the solenoid, the magnetic flux density at the center of the solenoid. So magnetic flux density at the center of the solenoid. So from that equation, B is going to be equal to mu naught, which is 4 pi times 10 to the power of minus 7, then times N, which is 1.5 times 10 to the power of 3. The current is 3.5. That's just substitution. So 3.5 times 1.5 exponent 3 times 4 pi times, 4 pi exponent minus 7. I don't know why pi doesn't go with exponent. Okay. So I'll say times 4 pi times 1 exponent minus 7. So that is 6.59 or 6.597 by 10 to the power of minus 3 Teslas. I'll just write 6.6 times 10 to the power of minus 3 Teslas. Calculate the flux linkage in the coil. So we know that flux linkage, I said flux linkage has no specific symbol. Do not use the symbol for magnetic flux to mean flux linkage. So flux linkage is equal to NBA or burn, which is going to be equal to 6.597 times 10 to the power of minus 3 times number of turns was 160. Then the area was, what is the area? The area is 26 centimeters squared. We change it to meters squared, so that is times 28 times 10 to the power of minus squared, that is power 4. That is the area. Power minus 4 to change it to meters squared. So I will say 6.597 exponent minus 3 times 160 times 28 exponent minus 4. So that is 2.955 or approximately 3.0. So that is 2.955 times 10 to the power of minus 3, which is approximately 3.0 times 10 to the power of minus 3 Weber. Then C Roman 1, I cut off C Roman 1. It was too much repetition. The current in the solenoid in B is reversed. It is reversed in a time of 0.8 seconds. What does that mean? The time for just from 0 to maximum value in one direction should be half of this. So the time in one direction is going to be half of that. And remember, the e.m.f is equal to the rate of change of flux linkage, rate of change of flux linkage. So the time, so this is going to be flux linkage divided by the time. And we say that the time is going to be equal to 0.80 divided by 2. Or, okay, I'll just take it divided by 2. So the e.m.f is going to be the flux linkage or change in flux linkage, which is 2.955 times 10 to the power of minus 3 divided by the time it takes to change, which is 0.80 divided by 2, which is the same as 2.955 times 10 to the power of minus 3, then times 2 divided by 0.80. Normally, whenever the current is reversed, you can just multiply by 2 and leave the time as it is. Whenever the current is reversed. So this is going to be 2.955 exponent minus 3 times 2 divided by 0.8. So that is 7.38 or 7.4 times 10 to the power of minus 3 volts. Okay. Two long straight vertical wires X and Y are separated by a distance 4.5 centimeters as illustrated here. The wires pass through a horizontal card PQRS. The current in wire X is 6.8 amperes in the upward direction. Initially, there is no current in wire Y. This is a similar question to what we have already answered. On the figure 5.1, sketch in the plane PQRS the magnetic flux pattern due to the current in wire X. Show at least 4 flux lines. So I'm going to try and twist this, but they're supposed to be concentric circles. We imagine holding the wire with the thumb pointing in the direction of the current as illustrated by this diagram here. So the fingers fold in the direction of the magnetic field. The magnetic field are concentric circles around the wire whose separation increases as you move away from the wire. So we draw concentric circles. I always encourage my students to use a compass, but because this is a plane which has been twisted, I'll draw elliptical patterns. Those are 2. Then I'll draw the third one. Then I'll draw the fourth one. Okay, so I'm trying just to demonstrate. Of course, when you use a compass, it looks very nice. I'm trying to demonstrate that the field line, the separation between the field lines increases as you move away from the center of the wire. Then the fingers are folding in the direction of the magnetic field, and that is anti-clockwise. So the arrows should point in the anti-clockwise direction. The magnetic flux density B at a distance x from a long straight current carrying wire is given by B equals to mu naught I over 2 pi x. I said mu naught is permittivity of free space, which is supposed to be this, but it's no longer in this syllabus, so that's why I quoted it here. Calculate the magnetic flux density B at wire Y due to the current in wire X. So magnetic flux density is going to be 4 pi times 10 to the power of minus 7. The current was 6.3. And note that the magnetic field which reaches wire Y depends on the current in wire X. And also the magnetic field which reaches wire X caused by current in wire Y depends on the current in wire Y. So this is going to be divided by 2 pi times x, which x is the distance between the two wires, which is 4.5, which is 0.045. Okay, so the pi has cancelled and the 2 has also cancelled. So I'm going to just say 2 times 6.3 times 2 times 6.3 exponent minus 7. Because pi has cancelled, divide by the 2 in the denominator has cancelled and the pi, so I will just divide by 0.045. So that gives us 2.8 times 10 to the power of minus 5 Teslas. A current of 9.3 amperes is now switched on in wire Y. So now there is a current of 9.3 amperes. Use your answer in Roman 2 to calculate the force per unit length on wire Y. Of course, the force per unit length is the same. The force per unit length on wire Y is the same as the force per unit length in wire X. So force, we know that force is going to be Bill or Bill sine theta. Of course, the magnetic field is in the horizontal plane and the current is in the vertical plane. So the magnetic field is perpendicular to the current. So this is the force per unit length, F over L is going to be Bi, that is sine theta equals to 1 because the magnetic field is in the horizontal plane and the current is in the vertical plane, so they are perpendicular, which means sine theta equals to 1 or theta equals to 90. So this is going to be equal to B, I think B was 2.8 times 10 to the power of 2.8 times 10 to the power of minus 5 Teslas, then times the current, which is 9.3. It is the magnetic field caused by wire X, which reaches wire Y. Then we need the current in wire Y, which is that one there. So I say times 9.3, which is 2.60 or 2.6 times 10 to the power of minus 4 newtons per meter. The currents in the two wires are not equal. Explain whether the force per unit length on the two wires will be the same or different. Of course, the force per unit length depends on the product of the two currents, because if you look at this part here, force per unit length is equal to B times I. If I want force per unit length on wire Y is going to be B caused by wire X times I in wire Y. And if I wanted the force per unit length on wire X, it is going to be B caused by current in wire Y times current in wire X. And when you look at the equation for B, B is going to be mu naught. B caused by X is mu naught times I in X divided by 2 pi times the separation X. If you look at B caused by Y, this is going to be mu naught times current in Y divided by 2 pi times X. We notice that in all cases, the force per unit length is depending on the product of Iy and Ix. So, the force per unit length depends on the product of the two currents. In bracket, F over L is directly proportional to current in X and current in Y times current in Y. So it's the same for both wires. So it's the same for both wires. Or you could explain this by Newton's as third law, or by Newton's third law, the forces per unit length are the same. In magnitude but in opposite directions. So the forces are the same in magnitude, but they're in opposite directions. Okay, so I want part 20 to stop there. See you in part 21. Until next time, bye-bye.